Okay, so now we know a little bit about the different kinds of energy, and we know that most energy that's emitted by the sun is in the visible spectrum. And that's because the sun is hot enough that it's emitting white light. It's white hot. So now, to understand the greenhouse effect, we're going to need to know what happens to that energy when it reaches the Earth. Okay, so we've got this little cartoon here where we've got the sun up in the sky, Earth's atmosphere is this first layer, and then here's the Earth's surface. Okay, the sun is emitting visible light, right? We know that visible light has a short wavelength, something kind of like this. Okay, so visible light emitted by the sun travels from the sun to the Earth's surface, right? If it didn't, we wouldn't be able to see anything. So you can just look outside your window right now and see the visible light reaching the Earth's surface. We do know, thanks to the albedo effect, that some of that light is going to get sort of reflected, right? Some of it gets reflected. Some of this light gets reflected thanks to the Earth's albedo, but most of it is going to pass right through the atmosphere. Okay, once that light strikes Earth's surface, it heats the Earth's surface up. Right? Anybody who's walked across a hot parking lot on a hot summer day knows that sometimes this energy can be quite warm, right? Asphalt can get really hot during the summer. So that means that this energy from the sun is absorbed by Earth's surface. And we learned in our lab that on average, about 238 watts per meters squared of energy is absorbed by the Earth's surface on average. And we know also that the Earth must then re-emit an equal amount of energy. So now 238 watts per meter squared is a lot less energy than the sun is emitting, right? It's not enough to make the surface of the Earth glow red hot, but it is still emitting energy. So if we think about our electromagnetic spectrum, if it's emitting energy, but it's not energy that's got a short enough wavelength to be visible to the human eye, right? You're not going to have a parking lot glowing red hot because of the sun's energy. That means it's re-emitting energy that is in the infrared spectrum. It's got longer wavelength, lower energy. Okay, so lower energy, longer wavelength, infrared radiation is then emitted by the Earth's surface. Okay, so visible light is emitted from the sun, travels through the atmosphere. Some of it gets reflected off the atmosphere. Most of it passes right through and reaches the Earth's surface. Should also note that some of it just gets reflected off the Earth's surface itself, again with that albedo effect, right? But about 238 watts per meter squared on average is absorbed by the Earth's surface. That heats up the Earth's surface, and then because the Earth's surface is heated, it's going to re-emit an equal amount of energy. Now that energy, again, it's not enough energy to make the surface of the Earth glow, so that means it's emitting infrared radiation. All right, that longer wavelength infrared radiation is being re-emitted or emitted from the Earth's surface out sort of in all directions, right? So when that long wave radiation comes into contact with the atmosphere, something very important happens. Basically, in the atmosphere, this long wavelength long wave infrared radiation is absorbed by greenhouse gases in the atmosphere. So unlike visible light, which passes right through the atmosphere, the infrared light cannot pass through the atmosphere so easily. Instead, it is absorbed by gases in the atmosphere. Okay, so what makes different kinds of radiation more likely to be, transmitted or absorbed by a surface? All right, so whether radiation is going to be reflected or absorbed by, or even just pass right through material sort of depends on two things. One is the wavelength of the radiation, and the other is sort of the properties of the material in question. So consider a couple of very familiar examples. Glass, right? Window glass is a solid substance that visible light can easily pass through, right? We know this to be true because we can see through our windows and our windshields. And yet visible light cannot pass through things like wood, right? Like this table, right? So it's same energy, visible light can pass through some things and is blocked by other things, right? So that sort of depends on the physical properties of the material. But whether or not radiation is going to be reflected, absorbed, or pass right through stuff also depends on the wavelength. So for instance, radio waves basically, ignore a lot of like solid materials, right? So they pass right through the walls of buildings. And of course, X-rays, right? If we think about X-rays, right? The reason that we are interested in X-rays is that they allow us to see our bones. So X-rays can pass right through the skin and tissue that make up our bodies, but bones are denser than skin and veins and blood vessels. So X-rays can't pass through them. So in fact, these X-ray images that we're looking at are negatives, right? The outlines of bones are spaces where X-rays have not passed through your body and reacted with this surface that X-rays are made with, right? So you can see with a couple of these like pretty familiar examples that depending on the wavelength of energy and the physical properties of materials, it's going to decide whether or not energy can pass through stuff or be absorbed by it or be reflected by it. Okay, so when that energy, visible light, goes right through the atmosphere, right? The same greenhouse gases are in the atmosphere when that light's coming down, but because the wavelength is shorter, it doesn't interact with these gases in the atmosphere, passes right through them, and then it's absorbed by the Earth's surface. The energy that's emitted from the Earth's surface has this longer wavelength, low energy infrared radiation. That's a different wavelength of energy, right? This wavelength of energy interacts with greenhouse gases, and it gets absorbed by the greenhouse gases. When that long wavelength infrared radiation is absorbed by greenhouse gases, that causes them to heat up. And when those gases heat up, then they emit more long wave radiation sort of down, back towards the Earth's surface. They re-emit more energy. Okay, so this is the greenhouse effect. It's this tendency of gases in the Earth's atmosphere absorbing long wave infrared radiation that's being emitted by the surface of the Earth. So these greenhouse gases in the atmosphere act as like a blanket, right? They're sort of insulating the Earth by catching some of this long wave radiation, getting heated up, and re-emitting more heat energy back down towards the Earth's surface. Okay, so here again, just a little tidier recap. We've got the sun, so hot it's emitting visible light. In fact, it's emitting 3.8 times 10 to the 26 watts of it. That's coming from the sun all the way to the Earth. Some of it gets bounced off the atmosphere, and some of it gets bounced off the Earth's system, right? So the average albedo for the Earth, remember from your lab, it's about 30%, so only 70% of the sun's energy gets into the climate system. That value is on average about 238 watts per square meter of energy that gets absorbed by the surface of the Earth, and that's not enough energy to make it glow red hot, but it's still emitting radiation. It's just emitting infrared radiation, right? Radiation that has got a longer wavelength than red light. Okay, that infrared radiation is emitted out of the Earth's surface into the atmosphere, but longer wavelength infrared radiation, remember lambda is a symbol for wavelength, this longer wavelength infrared radiation cannot pass through the atmosphere. It's instead absorbed by greenhouse gases. The molecules of those gas get heated up because they're absorbing energy, and that causes them to emit more radiation, more energy back down to the Earth's surface. So in this way, the greenhouse gases in our atmosphere act like a blanket that keep the Earth warm. And remember, they keep the Earth from being a frozen block of ice in space, right? They keep it much warmer, and they keep it warm that, such that we can live, such that we have liquid water on the surface of the Earth. They are so important to life on Earth that it is mind-boggling. We would be really, really in trouble if we didn't have greenhouse gases in the atmosphere. Okay, so what are these greenhouse gases? What is our atmosphere made of? It has three main components. So the atmosphere is mostly made up of these three gases: nitrogen, oxygen, and a gas called argon. Nitrogen makes up about 78% of the atmosphere. Oxygen makes up about 21%, and argon makes up about 1%. Okay, so you might have noticed that pretty much adds up to 100%. So what are the greenhouse gases, right? Where is there room in here for greenhouse gases? Turns out that greenhouse gases make up less than 1% of the atmosphere. There's a very, very small amount of the atmosphere that is made up of these greenhouse gases. Okay, what are the greenhouse gases? Well, the greenhouse gases there are three main greenhouse gases. One of them, you may be surprised to learn, is water. So water vapor, H2O, clouds. Clouds are very, very good insulators. If you've ever noticed, if you're a big camper or anything, when there's cloud cover at night, it usually stays much warmer. Okay, and now, so water vapor varies quite a bit in the atmosphere. It can be as much as like 3% of the atmosphere. But that's locally, right? So we live in a pretty arid place. There's obviously not 3% of the atmosphere made up of H2O here. So water vapor varies quite a bit, but it is one of the most important greenhouse gases. Now, the next one is carbon dioxide. Carbon dioxide, CO2. And this makes up only 0.04% of the atmosphere. Finally, we have methane. Methane, which is its chemical formula is CH4. So it's 1 molecule of carbon and 4 molecules of hydrogen. And methane is very, very small. It's not a lot of it in the atmosphere. There's only 0.00018% of the atmosphere is made of methane. All right, so here you've got it. This very, very important greenhouse effect, right, that acts like a blanket to keep the Earth warm, right, to keep it from being this frozen block of ice in space. And although the greenhouse effect and the greenhouse gases are so important, they make up this very, very small percentage of the atmosphere. Most of our atmosphere is nitrogen, oxygen, and argon, and none of these are greenhouse gases. So visible light can pass right through them, no problem, and so can infrared light, which passes right through it. Greenhouse gases, however, water vapor, carbon dioxide, and methane, infrared light has a much harder time passing through them. It can't do it. It's got to get absorbed by them and re-emitted as more heat energy back down to Earth's surface. Okay, so carbon dioxide is perhaps the most well-known greenhouse gas because it receives a lot of attention in the news, right? Because carbon dioxide is emitted by engines that burn fossil fuels, basically petroleum, right? So carbon dioxide, CO2, this greenhouse gas, is a side effect of internal combustion engines, basically. And our modern society produces a lot of it. So it's received a lot of attention in news and in politics and in science because it's very important to try to understand what potential effects the human emission of carbon dioxide might have on this very important system that keeps us from freezing to death, right? The only problem is it possible that we can emit so much CO2 that it would actually cause the planet to be too warm, right? That's the crux of the problem that we want to try to understand for the next few classes.